Galactic bubbles are more complex than imagined. A group of astronomers has made intriguing new findings regarding the unique properties of enormous bubbles of high-energy gas that extend above and below the central region of the Milky Way galaxy. In a recent publication in Nature Astronomy, a team led by scientists from The Ohio State University revealed that the shells encompassing these structures, known as E Rosetta bubbles due to their detection by the E Rosetta X-ray telescope, possess a complexity beyond previous assumptions. While these E Rosetta bubbles share a resemblance in shape to the Fermi bubbles, they are distinguished by their larger size and higher energy levels. Together referred to as galactic bubbles due to their substantial scale and strategic location, they offer a captivating opportunity to investigate the history of star formation and gain fresh insights into the formation of our own Milky Way. According to Anjali Gupta, the study's lead author and former postdoctoral researcher at Ohio State, now a professor of astronomy at Columbus State Community College. These bubbles exist within the circumgalactic medium, the gas that envelops galaxies. Our primary objective was to gain a deeper understanding of the circumgalactic medium, a region crucial for comprehending the formation and evolution of our galaxy, explained Gupta. Many of the areas we examined happen to overlap with the bubble region, prompting us to explore the distinctions between the bubble and non-bubble regions. Earlier studies hypothesized that the heating of these bubbles was a result of gas shock as it expanded away from the galaxy. However, the recent findings suggest that the gas temperature within the bubbles is not significantly different from that outside of them. We were surprised to discover that the temperature within and outside the bubble region was the same, Gupta expressed. Furthermore, the study demonstrates that the brightness of these bubbles is attributed to the presence of extremely dense gas rather than higher temperatures compared to the surrounding environment. To conduct their analysis, Gupta and co-author Smita Mathur, an astronomy professor at Ohio State, utilized observations obtained from the Suzaku satellite, a joint venture between NASA and the Japanese Aerospace Exploration Agency. By analyzing 230 archival observations from 2005 to 2014, the researchers were able to characterize the diffuse emission of electromagnetic radiation from low-density gas within the galactic bubbles, as well as the hot gases surrounding them. While the origin of these bubbles has been the subject of debate, Mathur stated that this study marks the first step towards resolving the question. The team's findings strongly suggest that the galactic bubbles were initially formed by nuclear star-forming activities or the injection of energy from massive stars and other astrophysical phenomena, rather than through the activities of a supermassive black hole. Our data supports the theory that these bubbles are most likely formed due to intense star formation activity at the galactic center, as opposed to black hole activity occurring at the galactic center, Mathur explained. To further explore the implications of their discovery for other aspects of astronomy, the team aims to utilize forthcoming data from upcoming space missions to further characterize the properties of these bubbles while also developing novel techniques for analyzing their existing data. Scientists truly need to comprehend the formation of these bubble structures, so by employing different methodologies to improve our models, we will be able to better define the temperature and emission measures we are seeking, Gupta added. The research involved collaboration with Joshua Kingsbury and Sanskriti Das from Ohio State and Yair Krongold from the National Autonomous University of Mexico. NASA provided support for this study. Neutron stars' X-rays reveal photon metamorphosis. An astrophysicist from Cornell University has put forth a theory explaining the intriguing observations of polarized X-rays emitted by a magnetar, a neutron star known for its powerful magnetic field. The phenomenon, detected by NASA's Imaging X-ray Polarimetry Explorer (IXPE) satellite, revealed that X-rays of different energy levels exhibited different orientations of their electromagnetic fields. According to Dong Lai, a professor of astrophysics at Cornell, the peculiar behavior of the polarized X-rays can be understood through the concept of photon metamorphosis, a transformation of X-ray photons that has long been hypothesized but never directly observed. This effect arises from the intricate physics of quantum electrodynamics, QED, a successful theory that describes the interactions between electrons and photons at a microscopic level. Lai's research, published in the Proceedings of the National Academy of Sciences, builds upon calculations he made 2 decades ago in collaboration with Win Ho. They incorporated the recent observations of the magnetar 4U0142+61, located in the Cassiopeia constellation, made by NASA in November of last year. Quantum electrodynamics predicts that as X-ray photons pass through the thin atmosphere of hot, magnetized gas surrounding the neutron star, they undergo a phase called vacuum resonance. In this phase, the photons temporarily convert into pairs of virtual electrons and positrons, influenced by the intense magnetic field of the magnetar. This process, known as vacuum birefringence, in combination with plasma birefringence, leads to a 90-degree shift in the polarization of high-energy X-rays relative to low-energy X-rays, as explained by Lie's analysis. Lie likens the polarization of X-rays to different flavors of photons, with the sudden conversion from one flavor to another being an uncommon occurrence. However, under the extreme conditions present in the magnetar's environment, it becomes a natural consequence of the underlying physics. Interestingly, the EXP mission did not observe the polarization swing in another magnetar, 1 RxSJ 170,849.0 to 400,910, which possesses an even stronger magnetic field. Lie's calculations suggest that in such cases, vacuum resonance and photon metamorphosis would occur at much deeper layers within the neutron star. By interpreting the EXP observations of the magnetar 4U0142+61, Lie was able to provide insights into its magnetic field, rotation, and the composition of its atmosphere, which is likely to contain partially ionized heavy elements. Studying X-rays emitted by extreme celestial objects like neutron stars and black holes allows scientists to explore the behavior of matter in conditions that are impossible to replicate in laboratories. These observations contribute to our understanding of the universe's diversity and beauty by shedding light on enigmatic objects like magnetars. Lie believes that the observations made by EXP open up new avenues for studying the surface environments of neutron stars, promising further insights into these fascinating cosmic entities. Thanks for watching. Please consider subscribing.